Hey, I'm Max. Sorry for this taking so long to get out, but I'm going to be going over, walking through the problems of the Spring 2024 Physics 2 final. I'm going to, well, set my calculator to degrees, which probably is a good advice for the actual exam. Yeah, I'm just gonna essentially try and run through these. I've got the work over here, so you can follow along, and also be annotating this document with thoughts and whatnot. Okay, so first we have point charges located at a square, and we want the horizontal component on Q1. Now Q4 only has a vertical component. We'll get rid of that. And let's see. This is 1, 1. This is -2. So we'll expect this to get attracted here because they're opposite charges and repelled here. So essentially these two forces are going to be competing against each other. This is Coulomb's law, which is what we're going to be using here. So just looking at Q2, right? First of all, we can factor out a KQ1 just to make things a little bit easier. So Q2, that has a charge of 1. And I mean, we'll say this is negative because we'll keep it positive. It doesn't really matter. And then we divide by the distance squared. So this is a side length 10 centimeters, so 0.1 squared. And then we subtract this here. So 2 is the charge. And the distance here is going to be square root 10, or like 0.1 squared plus 0.1 squared, Pythagorean theorem. 0.14, that's square root 2 divided by 10, probably, yeah. Root 2 over 10. If you square that, obviously, you will maybe get 0.2? 0.02. That's not right. Yeah, that's obviously not right. Scoring that? Well, whatever. 0.14 scored. And then the important thing is that with this one, you're not actually getting the full force in the horizontal direction as we want. It's going to be split between this y direction, essentially coming down here, and then coming over here. So to account for this, this is an angle 45 degrees. We can take the cosine or whatever of 45. It doesn't really matter. So yeah, we'll do that. 1 over 0.1 squared minus 2 cosine 45 divided by, let's grab this number up here, squared. Get that very large number. 9, where are you? 99 times 1. And then we get this one. I know I probably screwed up the unit somewhere. I don't really care. It's this 0.26. Obviously, nothing else is going to be correct. And since it's just off by factors of 10, not a big problem. So yeah. Yeah, I never put in the units for the this here, so that probably did some damage to make this number too large. Whatever. Next. Okay, so we have a particle with an initial speed in a uniform electric field. It's going in this direction. It travels, and it turns around and goes in the other direction. Or rather, the electric field is going in this direction, and it's shot in this direction. Magnitude of the electrical field. A lot of times, when it's given the mass, I always say it's either conservation of energy or it's kinematics. And when we're dealing with x's, it's usually going to be those kinematic equations. So we start with, well, first I'll say we're given the electric field. Force is equal to mass times acceleration. Oh, geez. But it's also equal to the charge times the electric field. So if we ever need to find the acceleration for a kinematic equation, we just use Q E over M. So, okay, let's start with this. So the particle travels 1 meter and then turns around. We got the magnitude of the electric field. Okay, I remember this one. This one's actually like a relatively difficult kinematics equation, all things considered. So, 1 meter, what does this represent? Well, this represents the initial velocity. So I'll say V naught times t, and then obviously plus at squared over 2, or rather minus at squared over 2, we'll just say the acceleration there is negative. And if we were instead to, obviously we don't have acceleration here, we don't have time. Let's look at the velocity equation, see if that helps us. So we can say velocity at any time, which will be at 0 at our point of interest because it's actively turning around, is equal to the starting velocity plus a t. All right. And we're trying to find the acceleration here so we can get the electric field. Let's see. I want to actually check my notes for this one because this one is rather tough. All right. So sorry for stalling here. So yeah, what we can do here, and I actually will set both of these terms to be like a minus just because it makes calculations easier. And what we can do is we can essentially just redefine t here as v naught over a, right? Like so. So we put this to the other side, and then we can define as such. And this is difficult because there's 2 equations and 2 unknowns, so we have to plug one equation into the other and just see what happens. So if we plug this t in up here, we'll get v naught squared over a minus, let's see, v naught squared over 2a, I believe. And then that just gives us, a v naught squared over 2a. So now we have this one, or we have this one is equal to all this, and this v naught 0 is already solved. It's this 10 kilometers a second. So we have one, I'll just say, I'll keep it at v naught. And then here we can plug in this formula here. So v naught squared times m is equal to 2 times q times e. All right, let's plug that in and see what we get. So we're solving for this e here. So we'll put that to the other side. Yeah, we'll just put that to the other side. So v naught is 10,000 squared times m, which is 1.67 times 10 to the negative 27, divided by 2, divided by q, which is the charge of an electron, which is 1.6 times 10 to the 19th. And we get 0.52. So that's the answer. Okay, next question. So this question gives us a lot of random stuff, and it's frankly just not something to be intimidated by. Let's start from the back, right? We want the net electric flux through the Gaussian surface outlined here with length 15 meters, which encompasses the entire cylinder, and radius 3 millimeters, which also encompasses the entire cylinder. So effectively, we're encircling the entire cylinder, and we want the net electric flux through that. Let's see what we can do electric flux. This is the one that kind of jumps out, right? E naught times electric flux is equal to charge enclosed. So let me write that down. E naught electric flux is equal to charged enclosed. Now, remember that this Gaussian surface is enclosing the entire body we have here. And we're actually given the net charge on both the rod in the middle and the net charge on that shell outside. So literally the overall charge enclosed is going to be that like 2 picocoulombs or whatnot, whatever that is. And we just take that and then we'll divide by 8.85 and we'll get the answer. That's all it is. So they will, I guess, put all the stuff in this problem to confuse you, but sometimes it is just simple. Also, yeah, there were units there. I just ignored them, and it worked out. Okay, what is the electric field in the x direction at 0.3 meters? If you look on your formula sheet at the bottom, somewhere up here, here, we can see that the electric field is actually the negative derivative of velocity, or of voltage, sorry, and we're actually given voltage. The derivative, thus, is just the slope, and we want x equals 0.3, so we want the slope right here. Well, we can see it's 0.4 high, and dx is going to be 0.2, and again, the formula sheet, it's just negative, it just gives us -2. Electron moving electrical potential. We have a fixed big proton, and we have a electron moving towards it. And at a certain point, we want its speed. Again, we're given the mass, which is either conservation or position. Now, although this does involve positions, they're not actually required to solve the problem, and indeed they don't ask us for a certain position. So we can actually try the much simpler conservation of energy approach. Of course, it's down here, but there you go. And, you know, that's mainly due to the fact that here, electron is initially at rest, so its kinetic energy is 0. So for review, kinetic initial plus potential initial equals kinetic final plus potential final. So it's at rest, so kinetic, which is 1/2 or mv squared over 2, will be 0 because v is 0. And then we have this, so this is going to be k absolute value of E over R times E, because potential energy is just E times Q. Or sorry, V times Q. QV. I think that's on the sheet. Yeah, right there. And then we set that equal to the new potential energy, which has changed. So Ke, I'll call this R prime E, plus that mv squared over 2, and we're solving for that v. So what does this actually kind of factor out to be? Well, first of all, we're subtracting this term from this term. And the difference here is that this R half is 1/2 the initial R, so we can like put a 2 here. Real quick, let's talk sign. So we have this 2. If we subtract it here, it'll be negative. However, what also happens is this E here represents an electron, which is negative charge. So this whole, both of these terms will become negative, and this is absolute value, so that doesn't influence it. So both these terms are negative, which means we're actually adding this to the other side, and we'll get a positive result. So we'll end up just having K times E squared. So I'll just go, whoopsies, 1.6. What was it? Negative 19, I think. probably know this at this point, squared, and then divided by that original r, which is just 1 centimeter. All right, and again, we're trying to solve for this, so we'll multiply by 2. We'll divide by the mass here. And we'll square root. And we get 225. Perfect. Okay, sweet. This one got a little screwed up. We can look at the actual question here. They're just meant to be in parallel there. So let's draw it out real quick. So we have 1, 1, 1, and then again, these are just meant to all be in line like so. 1, 1, 1. So the capacitors, when they're in series like this, that's when they do the like inverse addition, and they do when they're in parallel like this, they just add up. So here, just for an example, it would be like 1 and then 1 over the first capacitance, which is 1, and then 1 over the second capacitance, which is 1. A little bit anticlimactic in this case, but I guess you'll see it here shortly again. So 0.5, 1, and then here, since they're all parallel, we just add it, so 3. Again, these are parallel, we add 1.5, 3, and then here, we're employing the same technique here, 1 over 1.5 plus 1 over 3, and we get 1. Equivalent resistance, once again, let's redraw the circuit. Start at A and then kind of like trace through things, right? Here you can see we split by 3s. So the easiest way is this is the shortest path, right? We split where there's just one resistor and it goes straight to B. And then we also split into a kind of choice between 2 resistors and 1 resistor. So I'll represent it like this. And then those both meet up and go through another resistor. Obviously, everything goes to B at that point. So it's either just one straight resistor to B, or a split where you have a path of 2 or 1, and then one more until you get to B. The resistors add oppositely. So what that ends up meaning is that here, when you add these two for 400, they become 800. And this stays as 400. This one can be 400. And this one can be 400. And then here, whereas before you just added them willy-nilly with the capacitors, let's add to this weird rule. 260, 400, 400. Here we can add 400, and then 1 over 666 plus 1 over 400 will give us that 250 that we want. Cool. Number 8. What is the voltage across R3? So we have a bunch of different things that we want to kind of walk around the circuit. So this one here is 20 volts. This is 10 volts. These are 200 each ohms. 100, and this is 100. So the first thing to notice, which way is the EMF going to be like driving the circuit? So you can see there's 20 headed this way, counterclockwise around the circuit, and 10 headed clockwise. So we'll say that overall that clockwise will dominate, and we'll kind of like look at everything in this direction. So what happens when we walk through the circuit? Well, we get 20. So we'll go 0. We'll say we get 20 initially from this. And then we go, there's only one I in this. We go through this resistor. So IR2, I can say 200 honestly, I2 or 100. And then we hit this 200, so I200. And then we hit this this EMF, and since it's going in the opposite direction, we actually subtract this 10, because again, overall, we're only going to have like 10 volts being driven through the system. And then obviously minus I 200 from this one as well. Now what this ends up being is it's like 10, that net 10 going clockwise here, or counterclockwise? Counterclockwise is going to be equal to I of 200 plus 200 plus 100, or 500. And then we divide 10 by 500. We'll say that it's 0.02 amps everywhere. So 0.02 amps. And we want the voltage across R3. So voltage is just equal to amps times resistance. The resistance is 200 times the amps, 0.02, and we just get 4. So that's the right answer. Okay. There's no current. Switch is open. Immediately after the switch is closed, what happens? Well, what the inductor does is it tries to resist changes in current. We know that there is no current anywhere while the switch is open, right? That means that this line through the inductor had 0 current. Immediately after the switch closes, the inductor says, I'm not going to let a current change happen immediately. I'm going to stay at 0 current. So this all has 0 current and we don't care about it. So effectively, we're just operating on this circuit. That's all we care about. And this is R1 followed by R2 and then back to the battery. All we care about. We can add those together since they're in series for 30 ohms. It's 6 volts total across all of these. And since V equals IR, that implies that there's a amperage of 0.2. This amperage is shared between these two, and multiply that by resistor R1 to get a 4 volt overall. Okay, this one's going to be hard to do without right-hand rule, really displaying on the camera, but we'll see what I can do. So a charged particle is going in a circle perpendicular to a magnetic field. So what this particle is currently doing, so at this current moment, it's at the top of a circle. It's kind of like cruising. So if it was on this side of the circle, it would be going directly this way. If it was on this side of the circle, it would be going directly this way. So that means you can kind of convince yourself that the velocity here is to the right. It's straight to the right. Now, it creates a circle instead of just going straight to the right. It's veering downwards. So that implies that it's actually being forced downwards. So V is over here and F is down here. So it's trying to go right, but it's being forced downwards from the magnetic field. And again, that just keeps happening. Here it's trying to go down and it's going to be forced this way, and it'll keep happening, forming the cycle. So when we have this velocity, so you can point your fingers to the right, we need to get this force, so a downwards pointing force. Now, the particle is negatively charged, which means we want to flip our right-hand rule, right? We actually want to look for a force going upwards, and wherever this magnetic field is headed to, like that's the one that will push it actually downwards, because negative just flips things. So curl the velocity fingers in, and you see that they're pointing into the screen, I guess towards the camera, but into the page for me, so one is correct. And yeah, the force is, again, heading downwards. What's the magnetic field at point P in microteslas? So let's look through all these. So X, hopefully you know, means it's going into the page. So if you kind of do your right-hand rule, right, stick your thumb into the page and curl your fingers around, you can see that this has like a clockwise direction, as of course will this one. And this will actually has a counterclockwise direction. This is stick your thumb towards you, curl your fingers. So if you actually like extrapolate the circle, where will they hit P? So this one, since it's heading clockwise, it will kind of hit P in this motion, right? You'll have a large circle coming around like this, and that's where it will hit P. This one, since it's just heading clockwise as well, it will kind of hit P at the top of its circle, just kind of like what we see here. And this one, since it's heading counterclockwise, it's almost balancing out this one, heading like so. And we want the magnitude of the magnetic field. Now, it should be clear that since this is all symmetrical, these two will cancel, or the x's will cancel at least, and you'll just have a y direction going down, like so. So we have an x, and we have a y. Now, let's use our formulas for magnitudes of magnetic fields with points. Where are you? Actually, we're just gonna do this, I think. Right? Yeah. No. Oh wait, yeah, we just want the magnetic field. What am I talking about? Yeah, okay. We just want the magnetic field, which, what am I looking for? What am I looking for here? Hold, what's the question? 11? Okay. I was looking for a formula on the formula sheet. This is magnetic field due to a point charge, we know I over 2 pi r. I couldn't find it. Where is this thing? Oh, of course, they're not points, they're wires into and out of the page. Yeah, so you use the long straight wire formula. So let's start with the x, because that's the only one that's influenced by like a single one. It should be simpler. So we'll start with that. So bx is going to be equal to mu naught over 2 pi. Each wire carries 3 amps, so multiply by 3. And this one is going to be a distance of 2 away, so we'll just say 2. Cm. Y is going to be a little more complicated. We'll solve for one of them, and then we'll multiply by 2, because again, they're each going in the same direction. But obviously, we go mu naught 3 divided by 2 pi, just like we did up there. Then we'll multiply by 2. And there's a few other things we have to do. So one is the distance. The distance isn't going to just be d. It's this diagonal here. And so what that ends up being, I don't want to solve this out, dude. That's going to be 1 over, and then, you know, Pythagorean theorem, it's like square root 2 squared plus 2 squared. It's square root h. Or, sorry, what am I doing? It's square root d squared plus d squared, or root 2 times d. There we go. And then another thing is we only want the y component here. We're only solving for that y component. So we will take this angle here. Again, this is a 45-degree angle because it's a square with d on all sides. So we'll just say like cosine of 45. Maybe it would have been more proper to take sine, but I frankly don't care. So let's multiply everything through here. U naught is, it's like 4 pi times 10 to the negative 7th. I'll divide out the 2 pi here. So I'll just go like this. So that's the little thing we're dealing with there. 2e minus 2. So this is 3e minus 5. And this is going to be, so it's this term times 2 times cosine of 45 times, or rather we can divide by root 2 and divide by d. Oh wait, we are given d. I didn't know why I thought we weren't given d. Surprise, surprise, it's actually the same exact number. And so if we want to find the main thing, what we're going to have to do is we're going to have to take that 3, square it, take that 3, square it, and so we end up getting, 2 of that 3 squared, or this value times square root 2, or this 42. Cool. All right, next one. So a magnetic field is coming out of the page with a certain magnitude. A circular conducting loop is placed into the page. What's the induced EMF? So let's look at the formula for induced EMF. Actually, I don't really like using this formula. There's just a few steps you have to take, and I think it makes it easier. So if they ask for induced EMF, you need two things. You need a magnetic field and an area. So you basically look at whatever one is changing. Here, B is changing. So you take the derivative of that, so dB dt. And then the one that's not, you can just place in like A. If none of these are changing, so say you're given a static B field in a static area, sometimes you'll have an angle that's changing, and so you'll just put the rate of change of the angle in there as well. So effectively, put the rate of change of whatever is changing, and for everything else that's not changing, just put in the actual value. I guess you don't really have to worry about angle if it's not changing, but yeah, here it's dB dt times A. If A was changing instead of B, you'd put B times dA dt. That's all you need to know. There's like 3 possible things you could change, and just keep everything steady otherwise. Enough yapping. So dB dt, that is minus 4t, just deriving that. And we want A, so the area of a circle is pi r squared. So pi r squared. Oh yeah, and then technically it is negative, so like you do have to put a minus sign here, but it usually won't matter. Like it's multiple choice, dude. So let's just solve this. So we have our negative 4. We'll multiply by time equals 2. Multiply by pi. And then we'll do squared, 0.05 squared. And we get this 0.0663. Boom. So we got a capacitor connected to an inductor, and that's happened. So yeah, when you see a problem like this, where you're given a capacitor with an initial charge, and a system is kind of set up, and stuff just happens through it, and you're given certain values and you want other values, a lot of times you should just look at the energy stored in these things. So this inductor, very simple energy formula. A capacitor, very simple energy formula. Because ultimately this is a closed system, right? All the energy starts in the capacitor and it'll oscillate between the two, but everything will be, it's going to always be the same value inside the capacitor and the resistor. This isn't like a RLC circuit where stuff dissipates. It's just going to go back and forth. So we'll start with the energy of the capacitor. So energy of the capacitor is 1/2 CV squared. Actually, I like Q squared over 2C here. 1/2 Q squared over 2C. That's what we actually have here. So let's calculate the overall initial energy of the system. So Q is this 100 E negative 6 squared term times divided by 2 divided by C, which is this 10 E negative 6 term. So we get 5 E minus 4. And at a certain point, the charge, remember that we're really adding up the charge of the capacitor plus the charge of the inductor here. Except here, the inductor has a charge of nothing. It's just been added, or like it literally has nothing in it to start. So now let's calculate this at a certain point into the circuit. So when we calculate the potential energy of the thing, we'll do it like we did here, right? Q squared over 2C. So this is Q squared over 2C cell. And this of the inductor, it's Li squared over 2. So Li squared over 2. And that's going to just equal this initial energy value because the energy does not change. So let's do this q squared over 2c term. So it's just like this, except now the charge has decreased to a 60 from 100, down from 100. Bonk, bonk, bonk. And so we'll actually just take this and subtract this. So this is now equal to our second term, this Li squared over 2. So we'll multiply by 2. And so this is equal to Li squared. We want the I. So we'll divide out the L, which we're given here, for negative 3. And we can square root this to get 0.4, our current. Gaussian cube, something similar was on the last exam. So on the top face here, the magnetic field is given by B equals 4J plus 5K, and on the bottom is given by that. Find the other magnetic flux on the 4 faces. First thing to note, magnetic flux is going to be net 0 on all of the, on the thing as a whole, right? So what to realize there is that we'll find how much, based on the top and bottom faces, is coming net in or out, and then the sides will have to offset that. So let's try and do that. So top face, the magnetic field is given by that. Well, coming out here, well, this is going to be 5 in the direction coming out and 4 in this direction. It's going to look like this. In terms of magnetic flux, in terms of stuff coming out of here, of this edge, the amount coming out is really only proportional to the z component. So we'll say this is like 5. Similarly, this is 3 over to the y and 3 in the other direction, like this. But again, in terms of stuff just going into the cube, it's just going to be this 3. And when we add this up, we generally use the notation of like stuff going into as negative flux. So that means that overall we have a flux of 2 coming out from these faces. So that means that everything from the sides has to pick up slack, right? We want a net flux of 0, and from the top and bottom there's 2 coming out. So we want 2 coming in from the sides, hence this negative 2. Polarizing light. I think this is a pretty easy problem. So we start with unpolarized light. We'll say that initial intensity is just 1. When it hits the first polarizer, it always just gets halved. So we can pull up the formulas here. It always just gets halved initially. So that becomes, 1/2. Now, then we get hit. So it's all now oriented like so, straight up. And we're trying to move it to this with an angle of 30 degrees, right? And what that will essentially do is trigger this formula. So we had 1/2 initially, right? And we'll multiply that by a cosine of 30 degrees because that's how much the angle sort of has to change when it hits that polarization filter. That is a weird. Let me make sure I did my parentheses correct on this one. Okay. Oh wait, shoot. No, that's, oh man. Oh geez. I think 0.375 is probably right, but let's see, like this, just to double check. Yeah, there you go. And so now the light is coming out in this direction, in this 30-degree direction, and it's then being coerced into this 90-degree thing. So the change in angle from this 30-degree to this 90-degree is actually 60 degrees now. So it's even more apparent of a difference. So 60, we'll square it, and we end up with 0.94. All right. This is a funny little problem. So it says the angle of incidence at the AB boundary. So that's the angle, oh Jesus, right. That's the angle coming in here. So this is 45 degrees. And we want the angle of incidence at this CD boundary. So this angle coming out here. So let's start by doing this the dumb way. So when we kind of solve with Snell's law here, right here, we can just kind of go step by step. So we'll start in A, which is NA, and then we know this is sine of 45 because that was given. And then we'll set that to NB equal to NB, and we'll say sine of theta B. So what's interesting is this angle here, which we get from Snell's law there, is actually equal to this angle here, which we'll use for Snell's law additionally. So we'd actually use this formula NB sine B, or lambda B, or theta B, and we'd set this equal to NC sine of theta C, right? And, that would end up, we'd actually set that equal to this angle, again, going to be the same as this angle here, so we can stop here. But you can imagine that we then set this equal to the D part and whatnot. And because these angles are always the same, coming out and coming in, we can just make this whole chain. And honestly, we want to solve for this, and we're given this, so we can literally just ignore this middle term. So, well, we're solving for this. So let's go sine of 45 degrees, multiply by NA 1.2 and divide by NC 1.1. Inverse sine up here. And we get 50.47. All right, a small object is located on the central axis of a spherical convex mirror. So that's something like this, whose radius of curvature is 80 centimeters. So we're just going to use this formula. If the object is a distance 40 centimeters from the mirror, how far away is the image from the mirror? Now, for mirrors, a convex mirror, the radius of curvature is 80, but the focal length, we essentially treat this as negative, right? We can even treat this as negative. The idea here being that I like to think about it like anything that scatters out light beams. So here with this convex mirror, you put in some light beams and it scatters them around, whereas with a concave mirror, it groups them together. So anything that groups stuff together, whether it be a lens, so say like a converging lens, this will do a similar thing. I think this is not a converging lens. This is the converging lens. This will do a similar thing where it groups stuff together. That has a positive focal distance. Anything that splits stuff like this, or a diffracting lens, diffusing lens, I don't know, they will have a negative focal distance. But yeah, for this one, it's going to be a negative focal distance. So we'll use this formula here, 1 over f. And we know f is going to be like negative 0.4. We'll just do it in centimeters, so negative 40 is equal to 1 over p, which is the actual distance, so 1 over 40, plus 1 over I, the image distance, and that's what we want to find. So we got negative 40, or rather 1 over negative 40 minus 1 over 40. We'll go 1 over this. So I is equal to negative 20. What this basically implies is that, the light came in and it got scattered around. And instead of, what you'd expect with a mirror where you have an object and it comes out in front, the actual image is kind of projected to be over here, 20 centimeters away. So that's the virtual image, again, 20 centimeters away. Okay, double lenses, not that bad. It's just applying the same formula twice. So we have a converging lens here and a diverging lens here. So focal length of lens 1 is 4. So since it's, again, converging, it puts rays together. We'll leave it as positive. And this one's 5 centimeters. And again, diverging, since it puts rays apart, we'll give it a negative focal length. It's 5 centimeters here, this distance, and the length between the two lenses is 10. What's the magnitude of magnification? So we just have to do every magnification individually, and then we can multiply them together. So let's start here with the first image. So again, this is the formula we're going to be using. So 1 over f, which is 1 over 4 for this first lens, is equal to 1 over 5, the distance here, and then plus 1 over I1, let's see, I'll call that the first image. So 1 over 4 minus 1 over 5. Boom, 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 boom. So that's 20. Now what this implies is that this image has, at this point, gone so far that this image has, at this point, gone so far. Oh, this isn't even like the right part of my notebook where I like keep all this work. I don't know what I'm looking at anyway. I know what I'm doing. I know what I'm doing. So anyway, image distance is I. So that means to the right, it's actually 20 meters to the right of this converging lens. So it's all the way over here, 10 centimeters to the right of the diverging lens. Okay, cool. Interesting. We'll go to the diverging lens. So 1 over that focal length, which we said was negative, is equal to 1 over p. Now, this image, this first image, I1, will act as p2. And normally with lenses, we say anything that's on the left, or any starting image that's on the left, will be a positive, right? We expect something to come in here, get diffused or whatever, and happy, happy, happy. Here, we're actually starting from the other side. We're starting on the wrong side. So this is actually, instead of being, say 10 this way, it's actually negative 10. So a negative value here, and then obviously plus 1 over I, 2. So 1 over negative 5 minus 1 over negative 10. We get that. Divide, bump, bump. This is negative 10. Let's say this is negative, this was what, negative, or this was 20, flat 20. And this is negative 10. So that's saying that this is going to be 10 centimeters backwards, not on that side of the image, but again, just gonna be heading back this way. And the important thing here, m equals negative I over p. So the m total is just going to be like the m of lens 1 times the m of lens 2. So, you're just going to use this formula here. First, let's do m of lens 1. That was 20 divided by p1, which it started off as 5 up here. And then multiply negative new I was negative 10 is what it started at. So I'll just cancel out these equal sign or negative signs real quick. And then the old p, which ended up being negative 10. And we get 4. Boom, just like that. All right. So yeah, it's a weird behavior for sure with this one being negative 10. Just interesting. All right. Slits, I think this one's also fairly easy. We have a few formulas. You just have to know what the variables are and then just kind of plug in. So what is this? 2 slits. We're using one of these 2 formulas. Let's see. 500 nanometers, center slits, 2 meters away. The separation between the central bright spot, that's m equals 0, maximum, and the next bright spot is 1 centimeters. So we're looking for maximums, right? Bright spots. And that central one is represented by the m equals 0. So d sine theta equals m. D sine theta equals m times wavelength. Yeah, again, this m, that central one is 0, and that next bright spot is going to be 1. So we're really just solving for 1 because that's the separation between like 0 and 1. It's just 1. So we're just solving for d sine theta equals wavelength. All right, and the separation between the slits, that's actually the d. So we're going to be solving for that. And so we know that d is going to be equal to wavelength over sine theta, and we have the wavelength, it's 500. But how do we solve sine theta? Let's think of it as a kind of triangle. So this is going to be like our 2 slits or whatever. Say they're projecting light The screen is 2 meters away, right? This line here, 2 meters. And we see that the distance is 1 centimeter. I'll say 0.01. We can use inverse tangent to get this angle here, right? So if we say inverse tangent 0.01 over 2, we'll get that angle. We can then, of course, sine that angle if we'd like to get 0.005. You know, we can kind of see we're on the right track. It's a nice value there. You know, we can do something like this, and basically we get 100. If you applied the scaling from nanometers there, I bet it would have been crushed down to a small value, at which point, I don't know. But you can see. I guess you do have to account for units on this one. That's true. But you can trust me, this is the right way to do it. You just have to account for nanometers here, and this was correct, but nanometers. You'd get it. You'd get it. Okay, so we have a single slit diffraction. So we have the 6 minimum and the central maximum, and the distance there is that with the screen going away, wavelength. What's the distance between the 6 minimum? Okay. Let's do this. So it's a single slit. This only looks for minima. A sine theta equals m. A sine theta equals m lambda. Now, they say that the 6 minimum and the central maximum, so that represents an m of 6. We're solving for a, which is the unknown, and that's actually the width of that one slit. So that'll be m boom over sine theta. Now let's draw out our little diagram again, because we have a bunch of extra information. So we'll say this is our one little slit. The screen is 1 meter away, and the difference is 0.02, that's centimeter difference. So again, we'll just do something very similar, 0.02 divided by 1. There gives us our angle. We can tangent that angle, and we get 0.02. Or I don't want to tangent that angle. Oh my god, I did something really stupid. Sorry, tangent inverse 0.02 divided by 1. And then sine that. I think this might just represent the idea that sine equals tangent at these very small angles. But yeah, it's going to be 0.02. So here we have m, which is 6, and times a wavelength of 700 times 10 to the negative, who cares, divide by our sine, which is 0.02, and we get a big number, because I didn't scale for units. Whoop-de-doo. So yeah, we'll say, you know, some factor of that is going to be the thing, the distance between the two things. It's probably going to be like 0.21 or something. And now, or something even smaller likely. Then now we want the 6 minimum and the central maximum if the wavelength is 400. So essentially we're calculating the same thing. So now we know that's A. A is fixed. And we want to actually know the distance, which means we're solving for the sine theta term. Sine theta is equal to m whoop over A, which is this value here. So again, m is 6. I'm still looking for that distance, 6 minimum and the maximum. Wavelength is now 400. We'll divide by this big number here to get that, and we'll inverse sine. So at this point, we have our angle, right? And I mean, you could honestly just stop here and be like, it's probably close enough. We can double check. So at this point, we have our angle, right? The board is still 1 away, and we want to solve for this. Now, tangent gives you that question mark over that 1. So if we just take the tangent of this, we don't even have to multiply by 1, but, you know, for thoroughness, we would multiply by 1. Again, it's just pretty much the same as that sine, but it's 0.011. If I had done units correctly, would be 1.1. Yeah, that's about it. Good luck, everyone. It's 9:51. Don't stay up too late. Hopefully you're not watching this too late. I'm releasing this, frankly, too late, so I guess you already are. So go to bed. Is what I'm trying to say. If you're listening to this, go to bed. All right. Good luck, everyone.